Taylor series. We'll let a and x be two distinct real numbers and let j be the closed interval with endpoints a and x. Suppose that the function f possesses continuous derivatives of all orders on j. Then by Taylor's theorem, we have for all n greater or equals to 1, we get this, where a naught equals f of a, ak equals f to the k of a over k factorial, k equals 1 up to n minus 1, and c lies between a and x, thus as such. And if for a particular value x, that f to the n of c over n factorial x minus a to the n tends to 0 as n goes to infinity, then for this value of x, the infinite series here converges, and its sum is f of x. We can write f of x as such, where a of naught equals f of a of k again equals f to the k of a, k factorial. And this is Taylor series of f of x about x equals a. Now here's an example. Or let f of x equals e to the x for all x. Then f and all its derivatives are continuous at all points of our reals. We'll let x be any non-zero real number and apply Taylor's theorem on the closed interval j with endpoints at 0 and x to obtain this, where c is bound between x and 0. Now we can easily check that f of 0 equals 1, f to the k of 0 equals 1 for all positive integers of k, and hence the above equation reduces to this for c contained within this interval here. Now e to the c x to the n over n factorial, its magnitude is less than or equal to e to the magnitude of x, and x the magnitude of x to the n over n factorial for any given fixed real number x, which this goes to 0 as n goes to infinity. Thus for all r containing x, f of x equals e to the x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on, which equals x to the n over n factorial. And this expression can be used to obtain the real limit alpha be any real number. This can be used to obtain a real limit. Let alpha be any real number and choose a position integer q such that q is greater than alpha. Then for x greater than 1, we have 0 less than x to the alpha less than x to the q. Now as x goes to infinity, x to the q goes to infinity, and e to the x goes to infinity. What happens to this quotient? Well, if x is greater than 1, then e to the x is greater than x to the q plus 1 over q plus 1 factorial. Combining this with f of x above and along with our bounds, we get this, i.e. this for x greater than 1 as x goes to infinity. Now q plus 1 factorial over x goes to 0, and therefore using a sandwich rule, this too must go to 0 as x goes to infinity. It is therefore clear that as far as the limit is concerned, the exponential dominates the power. The corresponding rule for logarithms is that for all beta greater than 0, we get this relationship here within this box. This can easily be deduced from the sandwich rule for alpha equals 1. We see that x e to the minus x goes to 0 as x goes to infinity. Now we write x equals beta t, where beta is greater than 0. As x goes to infinity, t goes to infinity, and this goes to 0. Therefore, this goes to 0 as t goes to infinity. Now we write t equals the logarithm of gamma, so that e to the t equals gamma, and the relation becomes logarithm of gamma over gamma to the beta goes to 0 as gamma goes to infinity for beta greater than 0. Now we let f of x equals ln of 1 plus x, where x is greater than minus 1, and use a equals 0. In Taylor's theorem, first we let x be any real number such that x is between 1 and 0, and its absolute value is between 1 and 0. Then f and its derivatives of all orders are continuous on the closed interval with endpoints 0 and x. Using Taylor's theorem, we get this, where c is contained within x and 0. Now by differentiating, we find that f to the k of t equals this, for k equals 1, and so on and so on. Now therefore f to the k of 0 equals minus 1 to the k minus 1, k minus 1 factorial. Thus we get our, by Taylor's theorem, we get this here, which with this c is bound between x and 0. Now if our x is between 1 and 0, then we get this. Now because 0 is less than c, and c is less than x, and x is less than 1, then x to the n goes to 0 as n goes to infinity. Hence 0 is less than x, which in turn is less than 1. Then f of x equals ln of 1 plus x, and expanding our Taylor expansion is this, which is the expansion of ln 1 plus x with x equals 1. Right, in this bounds here of 1 over n, where 0 is less than c, and which is in turn is less than x, which equals 1. This remainder tends to 0 as n goes to infinity, and the expansion remains true for all x equals 1. If, however, minus 1 is less than x, and 0 is greater than x, then the remainder term is this. We don't know what happens as n goes to infinity, because minus 1 is less than x, and c is greater than x, and 0 is greater than c, which does not give enough information about this term. Moreover, if x is greater, if the magnitude of x is greater than 1, then x to the n over n does not go to 0 as n goes to infinity, and the series on the right hand side does not converge for any value of x for which our magnitude of x is greater than 1. Taylor's theorem can be used extensively to develop power series expansions for suitable functions. However, you must treat every series expansion with care. Don't take the series for granted. Don't take for granted that the series given here will have some value as f of x. The only way to use Taylor series safely is to check that what happens to the remainder term. As an example here, we'll let f such that we have a mapping from R to R, be defined that f of x equals e to the minus 1 over x squared for x does not equal 0, and 0 for x equals 0. And then f of x goes to f of 0 as x goes to 0, and f is continuous at the origin. Using the rule for composite functions, we see that f is continuous at all points of R. Now if x does not equal 0, then we get this, which this tends to 0 as x goes to 0, hence f is differentiable at origin, and f prime of 0 equals 0. Moreover, if f does not equal 0, then f prime of x equals this. So using the rule for differentiating composite functions, therefore, x does not equal 0, then we get this. And this tends to 0 as x goes to 0, and hence f double prime of 0 exists, and f double prime of 0 equals 0. Continuing, we can show that f to the k of 0 equals 0 for k equals 3, 4, and so on. Thus the series f 0 plus f prime 0x plus f double prime of 0 over 2 factorial x squared plus and so on consists entirely of 0, and its sum is 0 for all real numbers x. Hence the series here converges for all r in x and has sum 0, which is not equal to f of x if x does not equal 0. Right. That was Taylor's series.